Okay, this lecture is endothelial glycocalyx and blood flow part 1. Endothelial just means the lining cells of arteries. Glycocalyx means sugar coat. Glyco is sugar, calyx is coat. So it's a sugar coating along the walls of all your blood cells and all your endothelial cells. So a red blood cell here is also called an erythrocyte, has a negative charge on its outer surface. That negative charge is called a zeta potential. The little plus charges around here are just the ions in the blood, things like, potassium and sodium, for example. All right, and then the negative charges out here are things like chloride, for example. All right, well, the point is the negative charge on the RBC helps it to repel other RBCs so they don't stick together and cause clotting. But there are things with positive charges around them, like an IgM antibody, that's with an acute infection, that can overcome the zeta potential and stick red blood cells together. So when you have a severe acute infection, you're more prone to clotting, to thrombosis. Usually smaller antibodies like IgG antibodies won't have much of a pro-clotting effect unless they're present in really massive numbers with if they're severely high, let's say with multiple myeloma or something, but usually they're too small to overwhelm the zeta potential. LDL cholesterol is also positively charged and large enough in size that it'll stick RBCs together. Uric acid can stick RBCs together. Fibrinogen, the major clotting protein, will convert to fibrin when it's activated, and it'll stick red blood cells together. So those are all examples of bridging molecules, things that can stick red blood cells together by overcoming the zeta potential. Okay, when blood flows in an artery, you can see all these blood cells together, and they don't stick together. Normally they don't, because the red blood cells have a zeta potential. Negative charge repels other RBCs. Well, the white blood cells also have a negative charge, a zeta potential around themselves that repels the other blood cells. Okay, so that's how they avoid sticking together. Some interesting points here are that the red blood cell is about 7 microns in diameter, which is larger than a typical capillary, which is only about 5 microns in diameter. However, look how big this neutrophil is. This neutrophil is typically in the ballpark of around 14 microns, about twice as big as a red blood cell. Okay, so that's pretty massive. Red blood cells are much more common. Over 99% of the cells in the blood are red blood cells. So they're relatively rare, these guys, but when they have to go through a capillary, it's a bigger to do, because again, the capillary is smaller than the RBC. They really have to sort of squeeze themselves to go, under the limbo tree, if you will. Here's a lymphocyte, and what's interesting about it is the lymphocyte nucleus is the same size as the red blood cell. So if the red blood cells are in the same size ballpark as these nuclei of the lymphocytes, then you've got normocytic, normal size RBCs. If you're iron deficient, you can get iron deficiency anemia, microcytic anemia, whereby the red blood cells will be smaller than the lymphocyte nucleus. If the red blood cells are bigger than the lymphocyte nucleus, that would be megaloblastic anemia, and that would be like with vitamin B12 deficiency. Okay, so when a red blood cell floats through a capillary, it's got its negative charge around it, its zeta potential, and the endothelial glycocalyx, which means this lining on here's the endothelial cells. They line the artery, but they've got the glycocalyx, the sugar coat on top of them. And these right here are cholesterol sulfates. The cholesterol component is part of the glycocalyx extending towards the endothelial cell. It's really like part of the plasma membrane of it. But anyways, the glycocalyx sulfates, the yellow is the sulfur, the red is the oxygens, and those oxygens produce a lot of negative charge. So these contribute to the negative charge of this endothelial glycocalyx. I'll go into the structure of it in way more detail in just a moment, but just so you're aware of it, the endothelial lining has its own zeta potential, its own negative charge, and it's brilliant the way this is all designed. It prevents everything from sticking together. Okay, so here's a bigger picture of the glycocalyx. So this will be the lining of an artery, and the blood cells are going to be flowing through here. And this will be the endothelial cells right here. And this right here will be the glycocalyx, the sugar coating. So here's a close-up of it, and you can see here is the endothelial cells. That's their nucleus. This is the junction between two of them. They're actually kind of spindle shape in real life. And then here's the glycocalyx extending above them. Okay. These right here are the proteins of the glycocalyx. Typically, there'll be a core protein that extends upward, and then it's got all these little sugars attached to it. These sugars have a fancy name. I'm going to show you this in much more detail in a moment, but they're called glycosaminoglycans, GAGs, with repeating disaccharide units, mean repeating units of 2 sugars, okay? Dimers of 2 sugars repeated throughout. And they normally put up a lot of negative charge to keep the red blood cells far away. If the glycocalyx is damaged, all these negative charges from these sugars are stripped away, and then the white blood cells can bind to these adhesion molecules on the endothelial surface. That's bad. That's what happens with clotting and with inflammation. We're going to explain how all this works here in just a moment. Okay, so here's some red blood cells floating through a capillary. It comes from this paper here. And there's an endothelial glycocalyx. And the glycocalyx is kind of like jello. And it's also wet and moist. And it's real slippery. So the red blood cells slide right past it. And it has to be really well lubricated in order to get those big white blood cells, for example, to pass through here, through a capillary, which would otherwise be a pretty tight squeeze. And I also think it's incredible how all these components all work together. The endothelium making most of its glycocalyx, but it's also getting components made from the liver and made from the bone marrow. It's kind of miraculous. It's part of another one of the many reasons why I believe in God, because I study all this stuff, and it's so far beyond what a human mind could do. It's incredible. Okay, anyways, other things associated with the glycocalyx. There's other proteins on there like antithrombin 3 that very strongly prevent clotting. Okay, there's things to neutralize oxidative stress, and that's like superoxide dismutase. It'll have extracellular superoxide dismutase, so it'll block reactive oxygen species. You know, if there's some free iron in the blood, there's some omega-6 fat that undergo lipid peroxidation, this will help to neutralize that process. And we're not going to go into all the detail because there's tons of detail we don't need, but the main thing I think to get out of it is it's negatively charged, repels the RBCs, and it's very slippery. Okay, some of the things that make up that glycocalyx are these cholesterol sulfate molecules. So here's your typical phospholipid. Here's the phosphate component. Here's the lipid component. Your fatty acids. And here would be just a regular cholesterol with very little polar component, just a little hydroxyl group there on the tip of it. But when you got a cholesterol sulfate, the yellow thing is the sulfate, and then the reds are the oxygens. You can see it over here, sulfate in the center, and then it's attached to 4 oxygens. The original hydroxyl group or alcohol group of the cholesterol molecule, OH group, and then you've got the sulfur here with the extra oxygens on it. Okay, and then it's got this powerful negative charge, and that contributes to the plasma membrane negative charge, and it's going to contribute subsequently to the glycocalyx negative charge. So the glycocalyx is going to be built on top of these phospholipids. Notice also, cholesterol by itself is quite hydrophobic. It's entirely non-polar except for this hydroxyl group right here at the end. And that's partly why I can fit into the hydrophobic component of the phospholipid bilayer. And what's interesting about it is when you bind a sulfate to it, the sulfate then is polar. So this can travel in the blood effectively. You can't send sulfate by itself in the blood because it's too cosmotropic. Cosmotropic is like cosmos, like the cosmos, order in the sky, like God made order of the stars and the universe and all that. And the point is that sulfur causes, when they say causes ordering of bulk water, of aqueous solvents, what they mean is it causes them to form into like a jello, okay? And you don't want that happening in your blood. So what I'm saying is it's a good team that they make here together, your cholesterol molecules and your sulfate molecules, because the sulfate has just enough polar component to make this float in the blood, whereas the cholesterol can't travel by itself. It either travels in a lipoprotein or it travels with sulfate. And the sulfate can't travel by itself because it would thicken the blood, make it like jello. Together, they become amphiphilic. Amphi is like an amphibian, can live on water and can live on land. Philic is loving. So is can handle itself in water or land. And in a sense, what it means is it can be soluble in aqueous solution or it can be soluble in an oily solution. But this is going to be a really essential component because sulfate is going to contribute to the transport of all the steroid hormones. All the steroid hormones, estrogen, testosterone, you name it, they have a cholesterol-like backbone, and sulfate can help transfer them around. We'll get into the details of that later, but that's a very useful, important thing. Okay, here's another picture of what it all looks like to get a better sense of it. So this is the phospholipid bilayer. So this would be the cytoplasm over here. So this is the cytoplasm side of the plasma membrane of an endothelial cell. EC is for endothelial cell. This would be the hydrophobic center of the plasma membrane of the endothelial cell. And this would be the outer leaflet of the plasma membrane. This is the part facing the lumen of the capillary. The side that's away from it will sometimes be called the abluminum, okay? Okay, like when you abduct, you move your arms away from the body. All right, so this is the abluminal side, this is the luminal side. And then these core proteins extend up into this area over here, adjacent to the endothelial plasma membrane. And this is going to be called the Glyco-Calyx. Glyco, sugar, calyx is coating. It's called sugar because the majority of it, the bulk of it, is little repeating sugar units on all these things attached to the protein. They're called glycosaminoglycans, all right? The main one you're going to see is something called syndecan, and there's also glypican. And then cross-linking them going sideways are these hyalurans. All right, so those are some of the major components of the glycocalyx. Here's the red blood cells floating by. There's also albumin made in the liver, and that will get partly attached to this glycocalyx. These would be some neutrophils floating by as well. And then heparan sulfate is going to be the most common component, the sugar-like component of the glycocalyces. Okay, the other one you'll see some chondroitin sulfate. Chondroitin sulfate is better known for, it plays a major role in lubricating joints. You'll hear some people even take chondroitin sulfate as a supplement. Okay, heparan sulfate, though, is major loaded with sulfates and has a very extensive negative charge on itself, and that helps to repel the RBCs and the WBCs. So normally these proteoglycans, they stick up above the endothelial cell, projecting their negative charge. They're kind of like trees on a hill, for example. If you were flying in a helicopter over them, you would see the trees on the hill, and that's what the glycocalyx is to the endothelial cell. And they're also real slippery. There's this lady, she's smart. Her name's like Vivian Lowe, I think. She's got some good videos, and she came up with a good metaphor that they're almost like moss on a rock at the bottom of a stream. I thought that was a clever metaphor for describing the slippery nature of the glycocalyx, okay? Inflammation will cleave these proteoglycans, and then it'll leave these small attachment molecules. I'll have a better picture of it in a moment, what that's all about. But this is going to be something you can do to improve your health. That's why it's worth knowing this. There's a reason why I'm going through all this, because it's sort of the building blocks of understanding what's happening in an artery, and it's going to also contribute to you understanding what you can do to help improve your arterial health, improve your blood flow. So here's a heparan sulfate, and it's very much like the medication called heparin, the blood thinner. Lots of negative charges, so it prevents red blood cells from sticking together. Okay, you can see all these negative charges because of all these sulfates, sulfur with all these oxygen groups on it, tons of negative charge all over the place. That's a big zeta potential. Okay, now here's a drawing, I made to simplify things even more. Here's the core protein, okay, and then here is the glycosaminoglycan. Glycosaminoglycan, GAG it's abbreviated, is a polymer of a disaccharide. So a disaccharide is two repeating sugar units, and these together are called heparan sulfates. And at the very tip of them, they quite often have what is called a sialic acid, which is really just like a glucose with a carboxylic acid attached to it. The bottom line, it also gives off a negative charge. And I'm going to show you a picture of that in just a moment. But this is worth knowing. Plasma membrane of endothelial cell, of every single cell in your body has a plasma membrane, and it's probably going to have an endothelial, it's going to have some glycocalyx around it. Core protein with a bunch of heparan sulfates on there and negative charges. Now water is polar, meaning that it has a uneven charge on different sides of it. The oxygen component has a negative dipole, meaning a partial negative charge. The hydrogen component, H2O is water, has a partial positive charge. So the positive charges of water are attracted to the negative charges of the heparan sulfate, and there are other negative charges on the glycocalyx. For example, there's going to be some cholesterol sulfate in there as well. So this is how water gets attracted to the negative charges, and that's going to have a really special effect. We'll talk about that in just a moment. So again, here's sulfate. It's a sulfur molecule in the center with all these oxygens around it. Okay, the glycosaminoglycans and proteoglycans. The proteoglycans, they kind of look like little bottle brushes with their negative charges on them, and they almost like, I'll show you a picture in a moment, it's like a car wash. When it goes through a drive-through car wash and all the brushes rub against the car, that's kind of like what the proteoglycans do with their gags when they rub against the red blood cell that's passing through the capillary. Okay, so where does the negative charge of the endothelial glycocalyx come from? This is worth knowing. There's something called an easy water gel. I'll explain that in a moment. What that means is exclusion zone of water. and the water being like gel. We'll get into it. That comes from the work of Gerald Pollack. He's his PhD, did brilliant work on figuring out a fourth phase of water. We'll explain that in just a moment. Heparin sulfate, we just showed pictures of that with all the negative charges, especially coming off the sulfates. We showed cholesterol sulfate, and that also has a negative charge because of the sulfate with all the oxygens off the side of it. And a sialic acid has a negative charge because it's got a carboxylic acid attached to essentially very much like a glucose molecule. So that's where all this negative charge is coming from. Okay, so here are these proteoglycans with their negative charges sticking out from the endothelium. So you can imagine this being the plasma membrane of an endothelial cell projecting down. Here's the capillary lumen. And all these negative charges are seen by the red blood cell when it's passing by. So it wants to just squeeze right past them. It will not stick to them. Okay, so here's a nice picture of it. Here's a red blood cell going through a capillary. As a matter of fact, it would be more bended on itself, but just for the sake of description, this paper shows the red blood cell as being sideways. And you can see how the proteoglycans of Glycocalyx, here's the plasma membrane endothelial cell, they're a little bit smushed by the red blood cell, even more smushed or compressed by a white blood cell going through here because it's bigger, twice as big as the red blood cell. And their negative charge helps this red cell to kind of squirt its way along. So what's also interesting too, this is a little bit tough to see, but on a electron microscope, they got a red blood cell traveling through here. You can see it smushing the glycocalyx. Where there's no cell there, the glycocalyx then pushes back towards the center of the lumen. Here's a big honking white blood cell going through. You can see it really totally smushes the glycocalyx up against the wall of the artery of the capillary. So this is kind of interesting. Here's a picture where sort of they just isolated. They've taken it out and they've done it separately. You can see the glycocalyx, what it looks like, these little like bushes on top of the endothelial cells just below it. So here's the endothelials below it. Here's the glycocalyx above it. It's actually more profuse and diffuse in this picture. It's just that when they prepare the microscope slides, it's hard to maintain the whole thing intact. It's a little bit delicate. Okay, here's just a picture of sialic acids, what they look like. So the sialic acids, like this purple diamond, they're stuck on top of the glycocalyx. And they end up being important for a lot of other things. The thing that they're most important for, and we'll talk about this in a different lecture, is they are the identity of the cell, to prove that it is a human cell that belongs to you. And so this is N-acetyl-neuraminic acid, and then it has something, just call it Nu5AC. That's all you need to know, that's what you find in humans. And there's other types of sialic acids that are only found in other mammals, not at all in humans. And if you eat meat, beef or dairy, you can get some of your proteins contaminated by this stuff, and your body will be confused by that. Your immune system will attack it. So your metabolic system is too stupid, and it'll incorporate Nu5GC into its glycocalyces. But your immune system is smarter than that. It'll recognize the Nu5GC and think it's coming from a foreign source, another animal, and it'll attack those cells. So you can cause autoimmune disease from eating beef and dairy. That's one of the reasons for it. So we're not going to get into that today. That's actually a disease called xenosialitis. But just so you've heard of it now, we're going to get to that in a future lecture. The purpose of this lecture is more to emphasize the relationship to the glycocalyx. And the understanding of glycocalyx is real important for understanding blood flow, for understanding diabetes, understanding hypertension, and understanding cancer, metastatic cancer. So here's a sialic acid. Here's a glucose molecule. You can see it's very much just like a glucose molecule with a carboxylic acid attached to it, which gives it a negative charge. There's a little more to it than that, but that's the key point. Okay, healthy glycocalyx is a happy glycocalyx. The neutrophil or the monocyte, white blood cell, just travels right past it. Nothing sticks together. That's normal. That's how it should always be. In chronic inflammatory disease like diabetes, you have a thin glycocalyx, and you're more at risk to form atherosclerotic plaques in here, to form clots, and to have inflammatory cells break through this and get into the subintimal space, deep to the endothelium, into the tissues, causing inflammation. When you have a severe infection like sepsis, you can trash the entire glycocalyx, almost the whole, a huge amount of proteoglycans are cleaved off of this endothelial lining, and then they will travel to other locations. We're going to talk about that in a little while because that can cause brain damage and significant cognitive impairment. Okay, but one of the key points here is that here's a cancer cell. It's from this paper here about cancer cells. The cancer cell has to attach to the endothelial cell in order to pass between endothelial cells and become subintimal. So when a cancer cell goes from, let's say you have a cancer beginning in the breast, and it's now trying to spread to the liver, it has to attach to these adhesion molecules in the endothelial region, and then it can slip in between in the endothelial cells, go into the tissue, and start to grow. If you have an intact glycocalyx up here, it'll prevent this cancer cell from breaking through, and that's what you want. So that's why maintaining good endothelial health, glycocalyx health, prevents metastatic cancer cell from being able to attach to the endothelial lining of your arteries and break through. So here would be an intact glycocalyx, it comes from this paper here, and with the intact glycocalyx and its negative zeta potential charge, the cancer cell cannot attach. But if the glycocalyx is broken down for whatever the reason, diabetes will break it down, high-fat meal will break it down, sodium can weaken it, then the cancer cell can attach to these attachment receptors on the endothelial cells. And once it's attached to them, it can then get them to open up their tight junction between the endothelial cells, and it can break through and grow in the tissue beneath the endothelial cells, a subintimal space. So that's how metastatic cancer occurs. And so again, the point is, you keep this glycocalyx intact with all the healthy habits, you will help minimize your risk of metastatic cancer. Okay, that stuff about the 4 phases of water, it comes from the work of this scientist here, Gerald Pollack, PhD. He wrote a book about it too called The 4th Phase of Water. He has a bunch of YouTube videos that are quite good. So the point is, everybody learned in science class in high school that water has 3 phases. Liquid water or bulk water, water vapor, condensation, it evaporates, and then ice when it's frozen, go skating on. Well, it actually has a 4th phase where it's like jello, and this is sort of structured like a crystal, and the crystal nature of it becomes relevant because that's why it's called EZ, exclusion zone, that it pushes other things out of itself when it crystallizes. And most of the water in the human body is in this structured gelatin-like form. It's really not much more than the blood, the plasma is like water. When your urine, that's like water. Your saliva, that's like water, okay? Your tears, those are like water. But most of the water inside your cells, for example, in your cytoplasm and around your cells, outside your cells, in the extracellular matrix, it's actually in this gel form. Okay. The human body is about 2/3 water by mass, so that would be in the ballpark of around 60%, 60 to 66%. But if you counted the number of molecules, it would be about 98% water. And one of the unique things about this water is when it crystallizes, it'll actually push the positive charges to some extent away from itself, to some extent. And it'll sort of maintain negative charges along its outer surface, and that's called the exclusion zone. That's something that happens, during other types of crystallization as well. And so this is the crystal form. It's very similar to ice, but it's a little bit different. And it creates this negatively charged exclusion zone. And having all these charges all over the place, charge separation, that's what you have in a battery. And that provides energy to cells. They're able to harvest it to do useful work. So again, the blood flowing by is bulk water or plasma, whereas this is called exclusion zone water because it's excluding other charges and other types of molecules from itself to the extent that it can. Again, the reds are for the oxygens and the blues are for the hydrogens. And like you'd expect, the red's bigger than the blue because oxygen's bigger than hydrogen. Okay, and the separation of charge is what you see with the battery, and that enables the cell to do useful work. In other lectures, when we were talking about sodium and potassium, we talked about separation of charge on the plasma membrane being used to perform useful work. Okay. And this also shows here, again, this is the work of Gerald Pollack, showing that you've got this easy water, exclusion zone water, or gelatin-like water, 4th phase of water, all over the place in your cytoplasm, and it's creating all these little pockets of negative charge that the cell can use for energy. It's a form of potential energy. Okay, just a quick review. Here's the core protein in your plasma membrane, and it's attached to these repeating dimers of sugars called glycosaminoglycans, most commonly heparan sulfate. And you got the water dipoles with the positive charges attracted to the negative charge of the sulfates. Okay. That's gonna keep coming up all the time. And here's something cool about it. Inside of your joints, you got these same things, proteoglycans, meaning these big proteins attached to all these sugars like heparan sulfates and another form of chondroitin sulfate, which for our purposes is essentially the same thing. A lot of negative charge, and then they attract water to them. Attracting water to themselves. By the way, this guy's name is Andre K. Andre K. right here. He's got a great biochemistry YouTube channel, and I've learned a lot from his biochemistry video. So he's one of, there's other good ones too, but he's quite good. And I think he did a great job explaining how this works inside your joint. So when you take a step, his hand is showing the impact. It's going to smush down on your proteoglycans, and the water is going to bounce off for a moment during the impact. And then as soon as the impact starts easing up, the water reattaches because the charge on those water dipoles is attracted to the negative charge of the glycosaminoglycans, the heparin sulfate, the chondroitin sulfate. And that's how we have a shock absorber in our joints. And that's how we also have a lubricant, because this water lubricates everything so that your bones don't grind against each other. So what am I saying? The same things that protect your endothelial glycocalyx, they also protect your cartilage inside your joints, your menisci, your articular surfaces, and this is a major component of it. So that's kind of how it works with all this vegan diet, low fat, low sodium, is that the same thing protecting your arteries, it's also protecting your joints. It's also protecting your blood-brain barrier. So we're going to get to that later, but this is rather beautiful, isn't it? The water is a lubricant, and it comes on and off during impact of walking, and that protects the joint, and it lubricates it, and it's a shock absorber. Isn't that beautiful? That's an AO, academic orgasm. Okay, so here's the structure of cartilage. The cartilage, it'll have a central component of a hyaluronic acid, which we also saw was in the glycocalyx as a linking molecule. And you'll just have all these core proteins. You'll have the water attached to it. You'll have all the negative charges, especially chondroitin sulfate in the cartilage instead of heparin sulfate like it is in the endothelium. But the same effect. All these charges with water on the surface of it, making a lubricant and a shock absorber. If you decrease the sulfate content in the joint, you will be predisposed to getting osteoarthritis and damaging your cartilage. One of the spots you get sulfate from is just from being in the sun. That's another reason why you want to try to get in the sun a little bit. If you look at cartilage, cartilage has tons of water attached to itself. It's got a lot of collagen attached to itself. That's a triple helix protein. And then it's got lots of these proteoglycans. And then it's got a few cells, chondrocytes they're called. But there's not a lot of cells. It's relatively acellular. They've actually done studies of osteoarthritis patients in comparison with other patients, sort of like random fractures. And you'll see that you got a lot of less cartilage sulfate. So sulfate deficiency is part of what contributes to osteoarthritis and cartilage damage. High-fat diet also ends up having a harmful effect on cartilage. High-fat diet, this was done in mice, caused moderate osteoarthritis, including cartilage pathology and synovitis. Okay, this is just showing the same picture again, the plasma membrane, phospholipid bilayer, proteoglycan proteins sticking up with their heparin sulfates on them, keeping the red blood cells and the white blood cells away. Okay, and here's showing what can happen when you have inflammation. Or let's say you've got free iron in the blood. Let's say you got omega-6s in your blood and they're causing reactive oxygen species. And if they become too numerous, they'll start damaging this glycocalyx. Also, a high-fat meal will activate the neutrophils. It'll release myeloperoxidase. We talked about it in a previous lecture. I'll show you a picture of it in just a moment. And that's going to cleave the endothelial glycocalyx. It's going to knock off these glycosaminoglycans, and then these adhesion molecules are going to be exposed. I'll have a better picture of that in a moment. Also, abnormal blood flow with excessive turbulence and retrograde currents, that will also damage the endothelial glycocalyx, cause it to be cleaved, and then expose the adhesion molecules. Okay, so that's the end of part 1 about endothelial glycocalyx. In part 2, we'll just go into more detail about how it all works.